Okay, let's start with a recap of what we covered yesterday. Okay, so yesterday, one of the main things that we covered is um, when you have angle between two lines, L1 and L2, if they are intersecting lines, then there are actually two angles that we can find between the two lines. Namely, this bigger alpha here and the smaller theta here. And we always take the smaller one, and we always take the acute one. Take the acute angle. So that means when you want to solve for theta, for angle between two lines, you would use cos theta equals to b1 dot b2 divided by length of b1 length of b2 with modulus at the numerator. With modulus at the numerator to ensure that the answer you get for theta is acute. Okay. Okay, so that's what we covered yesterday for angle between two lines. And next, we also covered distance between two parallel lines. Here, of course, we are talking about two separate parallel lines, not coincident lines. So when we have a pair of separate parallel lines, the distance between the two lines will be a constant value, and there are some questions that might ask you to find distance between the two parallel lines. Okay. Now let's consider a pair of parallel lines here, L1 and L2. Okay. The distance between the two lines will be the perpendicular distance between them, which can be measured by, if I call this point P and Q respectively, then it will be, the PQ will be perpendicular to both lines. And the distance PQ will be the distance that we want to find. Okay. Most of the time, we will be given the equation, the vector equation of line L1 and L2. From the vector equation, you will be able to identify a point that lies on L1, let's call it A1 here. You will also be able to identify another point that lies on L2, let's call it A2 here. So the distance between the pair of parallel lines, it can be the distance from A1 to L2, which means you find the foot of perpendicular, let's call it F1 here, the foot of perpendicular from A1 to L2, and you would find this as the distance. Alternatively, you can also find the foot of perpendicular from A2 to L1. Let's call it F2 here. Then the distance from A2 to F2 will be the distance between the two lines. Okay, now let's continue with example 16. Okay, example 16 gives you two line equations. They ask you to find shortest distance between the two lines. Okay, so when you look at the two lines, you have to be observant about the direction vectors. Notice that these two direction vectors that I circled in yellow, they are scalar multiples of one another. Right, so you will have to tell the reader that we see that this is a pair of parallel lines, then only we use the method of distance between parallel lines. Because if these two are skew lines, then there will be a different technique used to find the distance between skew lines. Right, so we will have to first tell the reader that we can see that this is actually a pair of parallel lines. So what we can say in the working is, Note that -2, 4 minus 2 is equal to -2 times 1 minus 2, 1. So the direction vector of L2, this is the direction vector of L2, it is parallel to the direction vector of L1. Therefore, the lines L1 and L2 are parallel. Okay, so after showing that these two lines are parallel, then we can proceed to use the technique to find the shortest distance between two parallel lines. But since these two are parallel lines, we can visualize them this way. We have a point on L1 which is 0, 3, 1. We have another point on L2 which is 1, 0, 2. Okay. So you can either find the foot of perpendicular from 0, 3, 1 to L2 or from 1, 0, 2 to L1. Either way will work. And now for easier referencing, or in fact they have already named the points as A and B. Okay, then that's good. We don't have to name the points ourselves, but they have named the points A and B to be 0, 3, 1 and 1, 0, 2. Okay. Now I will use the foot of perpendicular from A to L2. I will use this yellow colored one. Okay, now let's introduce F. Let F be the foot of perpendicular from A to L2. And then we follow the usual procedure to find the coordinates of F. F lies on line L2. So OF will satisfy the equation of L2. So OF will be equal to use the equation of L2. That's 1, 0, 2 and minus 2 mu, 4 mu and minus 2 mu for some mu in R. And then referring back to our diagram up there, we want to get the vector AF, which will be then perpendicular to the direction vector of L2. Okay, so get the vector AF. OA will be put in the coordinates of A. Then notice that AF is perpendicular to line L2, which means AF dot with the direction vector of L2 is equal to 0. that you can sub in AF. Solve this equation, expand the dot product. And we get 2/3 as the specific value of mu. Okay, so what is actually our aim for the question? Our aim is to find the shortest distance. But the question doesn't really ask for coordinates of f. We are only interested in finding the distance between the two lines. Okay, so we know the distance between the two lines is the length of the vector AF. We are not so interested in OF, we are more interested in AF. So let's just sub into AF directly. Sub mu equals 2/3 into the expression for AF. Okay, then at the end we can find shortest distance between lines L1 and L2. Mention the word shortest distance at least. It is just the length of the vector AF. Which is just minus 1/3 squared minus 1/3 squared again minus 1/3 and squared again. And you get square root of 1/3 units. Okay, of course, this can also be written in other equivalent forms. Also acceptable. So example, this can be 1 over Z3, which is also the same as Z3 over 3. And that's it for this question. If everyone is done, I will continue with the next page, which is also the last page of the chapter. Okay, the last section of this chapter is reflection of a line in a line. So the line L, the one that is drawn thicker, is the axis of reflection. L1 is the original line, L2 is the reflection. Okay, so there will be a few steps to follow. I don't think you have to memorize the steps. You just need to understand what's going on, and then the steps will come to you naturally. Okay. Right, because these are all things that we have learned before in this chapter. We are just combining different techniques to be used in one go. Okay. I think it would be good if I start with a fresh diagram so that you can see what is a step-by-step procedure. Okay. The black line L is the axis of refraction. Okay. In the exam question, if they ask you to reflect a line in another line, I would say 90% of the time they are going to give you a line that intersects with L. Or else it will be very hard to do the reflection. Right, so I would say 95% of the time, when they would give you a line L1 that intersects with L. That intersects with L at one point, let's call the point, here they call it A, okay, let's call it A then. This A is the intersection point. Intersection point between L and L1. Right, and now L1 is to be reflected. Let's call this object. And naturally, you know the image will look something like this. And the image will look something like the dotted line there. Okay, okay, now, according to the step-by-step procedure, they say the first thing is to find the intersection point A. If L and L1 are intersecting lines, we will be able to get the intersection point. Okay, so after you get the intersection point, the next step to do is to use the fixed point on line L1 from the line L1's vector equation. For the vector equation of L1, you can read a fixed point on the line. And so you can visualize it as, they call it point P. And this is the fixed point on L1. Okay. Find the foot of perpendicular from P to L. Then extend this dotted line further to get the reflection of P, we call it P prime. Okay. So earlier we have learned the procedure of reflecting a point in a line. This is just applying the procedure that we have already learned before. You first find the foot, then making use of the fact that F is a midpoint of P and P prime, we can get the position vector of P prime. Okay. Then your reflected line that I'm drawing in orange now, this L2 is the reflected line or the image. The reflected line will have P prime being a point on it. And because P prime is a reflection of P. Right, so if P is on L1, then its reflection will be on the image. Its reflection will be on the image L2. So we know that P prime is a point on L2. So you can use P prime as the fixed point in the equation of L2. You can of course also use A. You can also use A as the fixed point in the equation of L2. It's up to you. Either P prime or A, either one will work as a fixed point. Okay, then you just construct a vector either from A to P prime or from P prime to A. Use either one of these as the direction vector of L2. Direction vector of L2, it only needs to be any vector that is parallel to line L2. So a convenient vector will be A P prime or P prime A. Either one will work. Yeah, so after you have the direction vector of L2 and also a fixed point on L2, you can happily write down the vector equation of L2, and then we are done. Right, so yeah, what I've said just now is the same as what is printed for you in the 4 steps. Right, so you don't really have to memorize the 4 steps here. As long as you know what's going on, you just need to reflect a point on L1 to become a point on L2, then get the intersection, then get the direction vector. At the end, just write the vector equation of L2. Right, then we are done. Okay. Now let's start the last example 17, which is a very long question. Example 17 is a very long question, and you would need your own paper to jot down the answers, because I don't provide you space here. Okay. Example 17, lines L1 and L2 are given as these two equations. There is an unknown A that appears here. Point A has position vector 2i minus 2j plus bk, another unknown B here. Given that the line L2 passes through the point A, so we have this information here. Find the value of A and value of B. In part 1, there's only line L2 involved. L2 involved, and the unknown A also appears in L2, so we only need the line L2. We don't need the line L1 in part 1. Okay. So the equation of line L2, let's convert it into a more familiar form. It's actually giving you as 4 plus A lambda like this, 6 plus 4 lambda, and 2 plus 9 lambda. Let's convert it into 462 plus A49 times lambda. Where lambda takes our real values. Okay, here's your unknown A. Okay. So it says L2 passes through the point A. L2 passes through the point A. In other words, A lies on L2. Okay, and what is coordinate of A? From the position vector, you know the coordinate is 2 minus 2b. 2 minus A with coordinates 2 minus 2b lies on L2. Okay, so we are 100% sure that OA will satisfy the vector equation of L2. 4 plus A lambda, 6 plus 4 lambda, 2 plus 9 lambda, for some lambda in R. Okay. OA is just 2 minus 2b. Okay. This equation holds for a particular value of lambda. And this equation is guaranteed to hold for a particular value of lambda because we know A is a point on L2. And this is an information that we know for sure. Which means that if you solve for lambda 3 times, there will be a consistent lambda. In other words, if you are able to find a value for lambda, that value of lambda will be applicable to all 3 equations. Then, of course, it's obvious that we should use the second component first because it only involves lambda as the only unknown. Okay. The first and third component will have A and B involved, and that is more complicated. So, of course, you would choose to start with the second component. Minus 2 equals 6 plus 4 lambda. This implies that negative 8 is 4 lambda, which implies that lambda is minus 2. Okay. And then you would equate the first component. 2 is equals to 4 plus a by minus 2. Minus 2 is a by minus 2. A is 1. B is 2 plus 9 lambda. B is 2 plus 9 by minus 2. B is minus 16. Right, so there we have it, values of A and B. And this is the end of part 1. And next I continue with part 2. Hence find the position vector of the intersection point of the lines L1 and L2. Okay. So here if they tell you to find the intersection point, then of course the lines must be intersecting, and then only they can ask you to find the intersection point. Right, so in this, when a question is phrased like this, we don't have to check ourselves whether the lines intersect or not. We don't have to check ourselves. If they ask you to find the intersection point, that means we can trust the question. We can trust the question and be confident that the lines are intersecting. Okay? There's no need to check whether or not the lines intersect on our own. There's no need to check. Okay. Right, then now let's look back at the information we have in the question. Okay, so earlier you have L2 and a point A on L2. Okay, now that we know L1 and L2 are intersecting lines, you can draw it this way. So L1 is the one in red color. Let's introduce the intersection point as point I for easier reference. Okay. L1, do we have the complete equation? Yes, we do have it. Yes, we do have it. So to find the intersection point I, you just need to equate the equations of L1 and L2. Okay, before that, let's just write down L1 and L2, the equations of the two lines in a more familiar form. Okay, L1 is R equals to 1 plus 2 mu, 2 mu, and you're given negative of 4 plus 3 mu. Okay, be careful with the negative being outside. That means you have to distribute your negative to the two terms. Which means 1, 0 minus 4 is the fixed point on L1. 2, 2 minus 3 is the one that is multiplied by mu. Mu is up. Okay, L2, I choose to just rewrite it. Earlier we already have it as 462 lambda A49. But then we already have A. A is 1. So I have 1, 4, 9. Now let's introduce I as the intersection point. Let I be the intersection point of L1 and L2. Equate the equations of L1 and L2. One plus 2 mu, 2 mu minus 4 minus 3 mu. Then we get three equations as usual. Okay, I tidy up it a little bit before I number the equation. Okay, this one I call equation 1, this one I call equation 2, this one I rearrange it a bit. Minus 3 mu is 6 plus 9 lambda. Okay, notice that all the coefficients are divisible by 3, so I tidy it up a little bit more. I divide everything by 3. Call this equation 3. Now pick two equations to solve for lambda and mu. Solving 1 and 2. Okay, since 1 and 2 have the same left hand side, we can just equate the two right hand sides. 3 plus lambda is 6 plus 4 lambda, which gives us minus 3 lambda is 3, and lambda is minus 1. So we have 2 mu equals to 3 plus negative 1. 2 mu is equal to 2. Mu is equal to 1. But since we already know that the lines are intersecting, we don't have to perform checking using the third equation. Since we already know that the lines are intersecting, there's no need to check using the third equation. So to find the point I, you just sub lambda equals to negative 1 into the equation of L2. Or you can also choose to sub mu equals to 1 into the equation of L1. Either one of these will work. In fact, both of these methods, whether you sub mu equals to 1 or lambda equals to minus 1, both of these methods will lead you to the same answer for the position vector of I. So you just need either one of this. Okay. So the next step, you can say OI. Since we have introduced I as the intersection point, OI will be understood as a position vector of the intersection. I choose to use equation of L1 this time. That's 1, 0, minus 4. Plus mu is 1 times 2, 2 minus 3. Okay, done. That's the final answer. If you sub lambda equals negative 1 into the equation of L2, you will also get the same final answer. Okay, part 3. Find foot of a perpendicular from A to L1. Foot of perpendicular. You can refer back to the diagram you have earlier. Let me just extend my line L2, make it longer. Now, foot of perpendicular from Jindra asked in chat, was it necessary to find both mu and lambda or just one was good enough? Well, actually, one of them is good enough. Yeah, actually, one of them is good enough. If you already know that the lines are intersecting, then finding one of them is good enough already. Okay. So going back to the diagram above, we want to find the foot of perpendicular from A to L1. L1 is a red one. L1 is a red line. A to L1 means it's this one here. So let's call this point as F. Let F be the foot of perpendicular. From A to L1. Maybe I should just paste the diagram down here so that I don't have to keep scrolling up and down. Okay, here's your L2. The purple line is L2. Okay. F lies on L1. So OF will satisfy equation of L1 for a particular value of mu. Construct the vector AF or FA, whichever you prefer. Minus by OA. Point A is, actually point A we also have the coordinates already. Yeah. Earlier at part 1 we say point A has coordinates 2 minus 2b. And what is b? B is minus 16. Okay, so just type in. You have 2 minus 2 minus 16. A is 2 minus 2 minus 16. So just put in 2 minus 2 minus 16. And that gives, just do a computation carefully. Make sure don't do any careless mistake. Although the computations are not difficult, it is tedious. There are many numbers to compute, so be careful in every step. Then notice that AF is perpendicular to L1, which means AF dot with direction vector of L1, which is 2, 2 minus 3, is equal to 0. AF is this thing. Dot with 2, 2 minus 3 is equal to 0. Compute your dot product. When you are using dot product, remember to write the dot there. The dot is necessary. This 36. and plus 9 mu equals 0. 4 plus 4 plus 9, you get 17 mu. 2 minus 36 minus 34. And mu is a nice number of 2. Okay, the aim of the question is to find position vector of the foot of a perpendicular. In other words, they want OF. They want the vector OF. Yeah, we have already introduced F as a foot of perpendicular, so OF will be understood. Okay. Sub mu equals to 2 into the expression for OF. Okay, where is the expression for OF is at the first step in this part. 1 plus 2 by 2, 2 by 2, minus 4 minus 3 by 2. Okay, done. Part 4 is to find vector equation of line L3, which is the reflection of L2 about L1. Okay, I use back the same diagram here. In part 4, they want to reflect L2 about L1, which means L2 is the object, L1 is the axis of reflection. L3 is the image. Here's your L3. This question, part 4, is actually quite easy to be done because the information that you need are already available from the earlier parts. Okay, earlier we have already found point I, and we have the vector OI earlier. That's the final answer for part 2. Okay, so point I, we already have it. Okay, just write it here. Point I have coordinates 3, 2, minus 7. Okay, point F, we also have it already. Point F have coordinates 5, 4, minus 10. So what remains to be found is A prime, which is just AF extended, and F is the midpoint of A and A prime. So let's introduce the meaning of A prime. Let A prime be the reflection of A about L1. F has been introduced earlier, so people will understand what F means. F is the midpoint of A and A prime. And so OF is half times of OA plus OA prime. After a simple rearrangement, OA prime will be 2OF minus OA, and then you can do your computation. Just be careful in all your computations. 10, 8 minus 20, 2 minus 2 minus 16. That's 8, 10, and minus 4. Then you also need the direction vector of your new line. And the direction vector of your new line can be either IA prime or A prime I, whichever you prefer. So suppose that I choose A prime to I, which is OI minus OA prime. But then we have enough information already to write down the vector equation. Vector equation of L3 is R equals to, don't forget your R. Whenever you state vector equation, you need R to be on the left hand side. Vector equation of a line is R equals to bracket plus lambda and mu have been used before, so let's use a different parameter here. Let's call it T, where T takes all real values. At the direction vector, you just use A prime I. You just use A prime I minus 5 minus 8 minus 3. As for the fixed point you can either use point A or point I, whichever you prefer. Sorry, I mean point A prime or point I. At fixed point, you can use either A prime or I, whichever you prefer. Since A prime is here, I just use A prime. That's A 8, 10 minus 4. Okay, done.